So today is day 16 sucked, so I'm making a follow-up and I'm listing that video and pinning on the comment with the link to it if you want to see it anyways. Okay, so here's the first problem. We have vector space of all real-valued continuous functions defined in this interval. We have to show that the mapping phi from the function xt to txt is linear. So essentially what we have to show is if we were to plug in this sum of xt and yt into phi, then it's going to be equivalent to phi of xt plus phi of yt. Okay, so now let's go ahead and try to show that. So according to the definition of the mapping, it's going to be t times the sum of xt and yt. Now we can use the distributive property, as we're working with the real valued functions. It's fairly easy to do algebra here. So now it just boils down to this too. So cool, we're done with that. We have a vector space E over gamma. We have a bunch of linear functions in E, and we have to show that the mapping phi from E to gamma r is given by this is gonna be linear. Okay, so let's begin by just noting down that any phi I is a mapping from A to gamma for convenience sake. Now the addition and other arithmetic for tuples is defined fairly easily, so I think we won't have much troubles. Let's begin with the first property for linear mappings. We have to show that it's going to be phi of x plus phi of y. So essentially we'll have a tuple again of 1 x plus y, and now we have the rest, and we have f r of x plus y. Now recall how every one of these functions is linear. That means that if we were to plug in x plus y into it, we're gonna get the sum of fix and fiy. So essentially we can split it into tuples and write it down as the sum of them. Plus f1 of y, and in the end we have a fr of y. Okay, I don't know why I wrote y here. It's supposed to be x in this tuple. So that essentially is just phi of x plus phi of y. So the first part that would make this mapping linear is proved. Now we need to prove the other one with the scalar. So we're to apply this. Again, properties of linear function are gonna come in handy. It's just gonna be lambda times fi of x. So I don't think I even want to bother writing everything down. I'll just write down the final result here. And it is going to be equivalent to just lambda times phi of x. Okay, cool. Now the last problem. We have a polynomial, we have a linear function in vector space E, we have a new function defined by pf that maps from the vector space to gamma, that is defined through this, and we have to find necessary and sufficient conditions on the polynomial such that pf becomes a linear function again. Okay, so let's look into pfx. Let's just take this over here. Now the thing is, we know that f is a linear function, and that will mean that if we were to just okay, that's phi, not f. If we were to just take f and sequence it continuously like this, till the end, we have something here, x. Okay, let's just tone it down like this. Then essentially, this entire function is gonna be linear. Now let me show that real quick. Let's take some function phi and input phi of x plus y here, and let's say that phi is a linear function. That will suggest that we can write it down as phi of x plus phi of y, and that in turn, since we know that phi is a linear function, can be written down as phi squared of x plus phi squared of y. So essentially, since we have proven the composition of two linear functions, I mean, they could be arbitrary, it doesn't really matter, it would just be not phi squared, it would be like phi times psi, but we're dealing with the same exact function here, so it doesn't really matter for us. So we're given the amount of times that's changed here by v, and thing is, since we're told that f is a linear function, so it will be this function. In other words, we know for sure that fxv is linear. In other words, if we were to write this down, the following will be true. Be true that this is just the sum of fxv plus fyv, and also the scalar property is gonna work in a similar manner. Again, we only need to prove the composition of two functions, because then you could just do it inductively. Okay, cool. Now let's look into the sum. We just have to prove that if we were to plug in different x's, then it's just gonna continue being linear. So I don't know why I copied this. Let's just rewrite it manually from v0 to n av here, f x v. Okay, and now let's plug in x plus y instead and see how it goes. So thing is, as we have deduced earlier, f of x plus y to the width power is going to be just this. Again, the power notation isn't like actual exponentiation in the classical sense, this is just composition of functions. It's like nice notation. Okay, now we can just split it into two sums. And guess what? If we were to say that this is equal to pf x plus pfy, yeah? This is essentially the first property that was necessary for us, because reminding you that the original input was x plus y, yeah? That's the first property. Now we need to prove the other one, or find conditions under which it's gonna be true, if it's not always true. Okay, so p of f lambda x. Again, let's copy the sum here. And we have f of lambda x composed 3 times. Now, as we have seen here, this is how it goes. So let's just take this here, and it becomes really handy. So next thing that we have, mind you that when we have vector spaces defined over something, in this case gamma is going to be a field, so multiplication is supposed to be commutative, so we can just pull out the gamma here, and the rest is going to be just p f x. Cool, I think we've proven all the properties necessary from us, so essentially there are no conditions that we have to prove. Any polynomial would do, and we don't really have any requirements from one for it to actually qualify as a linear function. That's a sketchy result. I'm not sure if I have messed up somewhere, so if you found an error, please write in comments. I'm really new to this stuff. Okay, bye.